The night sky is a grand illusion of emptiness. For every star you see, countless others remain completely invisible, hidden by forces and distances beyond comprehension. These are the universe's ghosts, real stars that exist just beyond the edge of our perception. They vanish behind cosmic dust. They are smothered by the glare of brighter neighbors, or they are so exotic that they defy ordinary detection. By the end of this journey, you will know 30 of the cosmos's most elusive stellar secrets, each a hidden wonder. We will explore a star that might be secretly orbiting our own sun, and another that is a cosmic Russian nesting doll, a star within a star. What does it truly mean for something to exist if we can never see it? Our first hidden star is perhaps the most personal, a ghost that might be circling our own cosmic neighborhood. This is the idea of Nemesis, a theoretical dark companion to our sun. The theory suggests our sun is not alone, that it has a distant, dim partner locked in a vast gravitational dance. This companion would not be a planet, but a small, failed star, perhaps a red dwarf or even a brown dwarf, so faint it has escaped every telescope. Its proposed orbit is almost unimaginably wide, taking it hundreds of thousands of years to complete a single loop around the sun, far beyond the frozen debris of the Oort Cloud. So why would scientists even entertain such a shadowy idea? The clue lies in the rocks beneath our feet. For decades, paleontologists have noted a strange, grim pattern in the fossil record, evidence of mass extinctions on Earth that seem to occur with a rough regularity every 26 million years or so. The Nemesis hypothesis offers a chilling mechanism. As this dark star swings through its distant orbit, its gravity would stir up the Oort Cloud, a vast shell of icy bodies at the solar system's edge. This gravitational nudge could send a shower of comets hurtling inward, a celestial bombardment with the power to darken skies and reshape life on our planet. It is a story written in craters and extinction layers, a cosmic clockwork of destruction. Yet for all its narrative power, Nemesis remains hidden in the truest sense. It exists only as a compelling hypothesis, a solution to a pattern that some scientists debate even exists. No direct observation has ever confirmed it. This makes Nemesis a perfect example of our theme, a star that lives in the realm of calculation and cosmic detective work, a ghost whose only evidence is the echo of catastrophe. It is a reminder that some of the universe's most powerful actors may be those we cannot see, whose presence is inferred only by the disturbances they leave in their wake. The Nemesis star is a ghost of gravity, its presence felt only through ancient scars. But what about a star that hides in plain sight, wearing a perfect disguise? Our second hidden wonder is not just invisible, it is a cosmic cannibal, a star that has consumed its own heart and replaced it with something monstrous. This is the Thorne-Żytkow object, named for the physicists who first imagined it. Picture a dying red giant star, a bloated, aging sphere of gas hundreds of times larger than our sun. Now imagine that deep within its fiery belly, at the very core where nuclear fusion should be raging, there is no ordinary stellar heart. Instead, a city-sized neutron star, the crushed, ultra-dense corpse of a dead sun, orbits silently. This is not a simple binary system, it is a stellar Russian nesting doll gone horribly wrong. The neutron star did not just get close, it was swallowed whole, plunging into the outer layers of the giant and spiraling down through its vast atmosphere until it came to rest at the center. There it sits, a diamond bullet encased in a hot, gaseous ocean. This union creates a freak of stellar physics. The intense heat and pressure from the neutron star's presence stir up exotic nuclear reactions in the surrounding gas, forging rare, heavy elements that normal red giants cannot produce. It is a hidden factory for cosmic oddities operating in secret. So why is this spectacular hybrid so hidden? Because from the outside, it looks almost perfectly normal. To our telescopes, a Thorne-Żytkow object appears as just another red giant, a faint, cool, reddish dot in the sky. The monstrous truth is buried deep within its light. The only way to potentially unmask one is to analyze its starlight with incredible precision, searching for the chemical fingerprints of those strange internal reactions, elements like rubidium, lithium, and molybdenum in unexpected amounts. It is a spectral whisper easily drowned out. To date, only a handful of candidates have ever been proposed and none definitively confirmed. They are the universe's ultimate impersonators, stars that are not what they seem, hiding a cataclysmic secret behind a veil of familiar, gentle light. They remind us that sometimes the most violent and extraordinary events are concealed within the most ordinary of shells. That stellar corpse at the heart of a Thorne-Żytkow object gives us a terrifying glimpse of a neutron star's power. But what happens to such an object when it is not hidden inside another star, when it is utterly alone in the dark? Our third hidden star is not one object but a class of them, and they represent a profound cosmic silence. These are the isolated neutron stars, the quiet ghosts of supernova. Picture the aftermath of a star's catastrophic death, a titanic explosion that scatters its outer layers across light years. All that remains is the crushed core, a sphere of pure neutron matter just 12 miles across, yet containing more mass than our entire sun. A teaspoon of its material would weigh as much as a mountain. For many neutron stars, this is not the end of the story. They become pulsars, spinning rapidly and beaming lighthouse-like jets of radiation across the galaxy, announcing their presence with metronomic precision. But some neutron stars are different. They are the ones that have grown old and quiet. Their rapid spins have slowed, their powerful beams have faded, and they no longer shout their location to the cosmos. They simply sit cooling. These are the universe's dying embers, and they are almost perfectly hidden. The reason is simple: they emit almost no visible light. Their surfaces, however, are still searingly hot from their violent birth, glowing at over 1,000,000 degrees. This heat radiates out not as the light our eyes can see, but as high-energy X-rays. To our optical telescopes, these stellar corpses are completely invisible, dark spots against a starry background. They are only revealed as faint, mysterious points of X-ray light, detected by space-based observatories like Chandra or XMM Newton. A famous group of these objects found relatively close to Earth are nicknamed the Magnificent Seven. They are middle-aged neutron stars a few 100,000 years old, and they are not pulsars. They emit a steady, soft glow of X-rays and a whisper of ultraviolet light, but nothing in the optical spectrum. Finding their exact location is a cosmic game of pin the tail on the donkey. Astronomers must match the precise X-ray coordinates to an empty patch of sky in optical images, confirming the source is truly dark. These hidden cinders are the silent majority, the final, fading chapter in a star's life. They remind us that the most common afterlife for a massive star is not a brilliant beacon, but a slow, dark fade into oblivion, a hidden monument to a violence long since past. That silent fade of a cooling neutron star is a lonely end. Yet there is a place in our galaxy where stellar existence is anything but lonely or quiet, a place where stars are hidden not by darkness, but by sheer, overwhelming brilliance and chaos. This is the very heart of the Milky Way, a region of such cosmic violence and density that it defies all intuition. At the center of it all sits Sagittarius, a star, our galaxy's supermassive black hole, a gravitational monster with the mass of 4 million suns. Around it, in a frantic, high-speed ballet, orbits a swarm of stars. We know some of their names, like the star S2, which screams around the black hole at speeds exceeding 15 million miles per hour, completing an orbit in just 16 years. But for every star like S2 that we can track, there are countless others we cannot see at all. They are the fourth category of hidden stars, those lost in the maelstrom of the galactic center. The first and most obvious obstacle is a thick, choking shroud of cosmic dust and gas that stretches for thousands of light years between us and the core. This dust blocks virtually all visible light, rendering the galactic center completely invisible to optical telescopes. It is like trying to see the details of a city street through a dense, perpetual fog. We peer through this fog using instruments that see in infrared and radio waves, wavelengths that can slip between the dust grains. But even when we pierce the veil, a second, more bizarre form of hiding takes over: gravitational lensing. The immense gravity of Sagittarius, a star, warps the very fabric of space-time around it. Light from stars behind the black hole does not travel in straight lines. It is bent and twisted, stretched into faint, smeared arcs. A star directly behind the black hole from our viewpoint might have its light bent completely around it, creating a distorted, circular mirage known as an Einstein ring. The star's true position and nature become a puzzle. Furthermore, the region is a stellar traffic jam of unimaginable density. Millions of stars are crammed into the central parsec, a volume of space where the average distance between stars is only a few thousand times the distance from the Earth to the Sun. In such a crowded neighborhood, the brilliant light from young, massive blue giants and the furious glow of heated gas drowns out the fainter light of smaller, older stars. They are lost in the glare, like trying to spot a single candle flame while staring into the beam of a searchlight. So, while we marvel at the few stars we can track whipping around the void, we must remember they are just the visible few in a vast, hidden multitude. The galactic center is a place where the universe itself becomes a magician, using dust, gravity, and sheer radiant power to conceal an entire population of stars in plain sight. A hidden metropolis swirling in the dark heart of our home galaxy. The galactic center is a cosmic blind spot of our own making, a place where our galaxy hides its own secrets. But there is an even grander, more fundamental blind spot in our view of the entire cosmos, a vast swath of the sky where entire galaxies full of stars simply vanish. Astronomers call it the zone of avoidance, and it is not a place of emptiness but of overwhelming obstruction. Picture holding a dinner plate edge on directly in front of your eyes. The plate blocks your view of everything behind it, creating a narrow band of blindness. Our Milky Way galaxy is that plate. We live inside a flat, disc-shaped spiral galaxy. And when we look out into the universe, our view in the direction of the plane of that disk is completely choked by its contents. This is the zone of avoidance, a thick band that encircles the entire sky, hiding perhaps a quarter of the distant universe from our optical telescopes. It is a wall built from the combined light of billions of foreground Milky Way stars, and more effectively from immense clouds of interstellar gas and dust that absorb and scatter visible light. Behind this luminous, murky veil, billions upon billions of stars in other galaxies remain perpetually hidden. Their combined light, which would paint the large-scale structure of the cosmos, is simply swallowed whole. For centuries, this zone was a literal blank on our maps of the universe, a frustrating gap in our understanding of how galaxies cluster and weave the cosmic web. Peering through this veil requires abandoning the light our eyes can see. Just as we use infrared to see the galactic center, astronomers point infrared and radio telescopes toward the zone of avoidance. Infrared light, with its longer wavelengths, can slip between the dust grains more easily. Radio waves pass through almost unimpeded. These tools act like cosmic sonar, pinging through the fog. And what they have revealed is astonishing. Slowly, painstakingly, surveys have begun to map the hidden architecture. They have found entire galaxy clusters lurking behind the Milky Way's bulge, massive conglomerations of hundreds of galaxies that were completely unknown to optical astronomy. They have traced the tendrils of the cosmic web, the vast filamentary structure that connects all matter in the universe, finding that it continues seamlessly through the zone. Every new detection is like finding a hidden continent on a map thought to be complete. These efforts are more than just filling in blanks. They are crucial for understanding the true motion of our own galaxy through space. By mapping the gravitational pull of all the mass, both seen and unseen, on the other side of the zone, we can better calculate our place in the grand flow of the cosmos. So, the next time you look at a stunning deep field image from Hubble or James Webb, remember that it is only a partial view. A parallel universe of stars and galaxies exists in a great hidden band across our sky, a blind spot imposed by our own celestial address, reminding us that to see the whole picture, we must learn to look with invisible eyes. That great cosmic blind spot hides stars in space, but our next hidden stars are lost in time. These are the first stars, the universe's original pioneers. Astronomers call them population 3 stars, and they were unlike anything that exists today. Born from the pristine, primordial soup of the Big Bang, they were composed of only hydrogen and helium, the 2 simplest and lightest elements. There was no carbon, no oxygen, no silicon, no iron. That purity made them fundamentally different and, according to theory, absolutely monstrous. Without heavier elements to help them radiate heat away, these first stars could grow to staggering sizes, perhaps hundreds of times more massive than our Sun. They would have burned with a ferocious blue-white intensity, living lives of incredible violence and brevity. A star like our Sun has a lifespan of 10 billion years, but a population 3 star would have consumed its nuclear fuel in a cosmic blink, perhaps only a few million years. Their deaths were not quiet fades, they were cataclysmic hypernova, explosions of such unimaginable power that they seeded the early universe with the first heavy elements, the very atoms that would later form planets, oceans, and life. This is why they are hidden from us, not by dust or distance alone, but by the deep time of cosmic history. Every single one of them is long gone, having died over 13 billion years ago. We will never directly see their light, so how do we hunt for ghosts that vanished before our galaxy even formed? Astronomers become cosmic archaeologists, searching for the chemical fingerprints these giants left behind. They point our most powerful telescopes, like the James Webb Space Telescope, at the most distant quasars, the brilliant cores of ancient galaxies whose light has been traveling to us for over 13 billion years. By analyzing the delicate spectrum of that ancient light, scientists can detect the faint absorption lines of elements scattered in the space between the quasar and us. When they find clouds of gas that contain only hydrogen and helium, with a complete absence of any heavier elements, they might be looking at material that was never touched by any star except a population 3. It is pristine space, a fossilized bubble of the early universe. Another promising hunting ground is in the faint, ancient dwarf galaxies that orbit our own Milky Way. Some of these tiny galaxies are thought to be cosmic relics, frozen in time from the universe's first billion years. Within them, astronomers search for stars that are incredibly metal-poor, stars with only the tiniest trace of elements heavier than helium. These ancient second-generation stars would have formed directly from the ashes of a single population 3 supernova. By studying their chemical makeup with exquisite precision, we can work backwards like forensic scientists reconstructing a crime scene to deduce the size, life, and violent death of the first star that created them. Each new metal-poor star discovered is a clue, a message in a bottle from the cosmic dawn. The hunt for population 3 stars is a quest for our ultimate origins, a search for the mythical giants whose spectacular deaths provided the raw materials for everything that followed, including us. They are the most profoundly hidden stars of all, visible only in the elemental echoes they left in their wake. The elemental legacy of those first giants gave rise to every star we see today, but not all stellar offspring achieved that brilliant destiny. Littering the cosmic landscape, especially right in our own galactic backyard, are countless celestial underachievers, objects that never quite made the cut. These are brown dwarfs, the failed stars of the universe. They form like stars from collapsing clouds of gas and dust, but they simply lack the necessary mass to ignite the sustained nuclear fusion of hydrogen in their cores, the defining characteristic of a true star. They are cosmic in-betweens, too massive to be considered planets, yet too feeble to be proper suns. A typical brown dwarf might be only a few dozen times the mass of Jupiter, and this modest size is the root of its profound hidden nature. Without a sustained internal fusion engine, a brown dwarf produces very little of its own visible light. After a brief, warm infancy fueled by the leftover heat of its formation, it begins a long, slow fade into obscurity. It does not shine, it merely glows with a dim, residual warmth. This glow is not in the spectrum of light our eyes can perceive. It is emitted almost entirely as infrared radiation, a form of heat. To our optical telescopes, even a brown dwarf drifting silently between the stars in our immediate solar neighborhood would be utterly invisible, a dark specter against a backdrop of brilliant points of light. For decades, they were purely theoretical, the universe's missing link. Their discovery required a shift in how we look at the sky, moving from the realm of visible light into the infrared. This is where missions like the Wide Field Infrared Survey Explorer, or WISE, revolutionized the hunt. WISE scanned the entire sky in infrared light, acting as a thermal camera for the cosmos. It was designed to see the faint, warm glow of objects too cool to emit visible light, and what it found was astonishing: a hidden population of cold, nearby brown dwarfs, some of the coldest and closest stellar objects ever identified. These discoveries revealed just how blind we had been. Some of these brown dwarfs, with whimsical names like WISE 0855-0714, are among the coldest known objects of their kind, with temperatures colder than a winter day on Earth, and they appear to be remarkably close to our solar system. In fact, several are estimated to be within a mere handful of light years from us, potentially closer than Proxima Centauri, the nearest true star. Think about that for a moment. There could be more of these failed stars within our immediate cosmic vicinity than there are proper suns, and we would have no idea if we only looked with our eyes or traditional optical telescopes. They are our ghostly neighbors, passing silently in the dark, their presence known only by the faintest whisper of heat they emit into the cold of space. Their discovery forces us to rewrite the map of our local stellar neighborhood, reminding us that what we perceive as empty space is often anything but. Our own neighborhood may harbor these cold, dark failures, but elsewhere in the galaxy, perfectly brilliant stars perform a far more theatrical disappearance. They do not simply fade, they are abruptly and completely erased from the sky for years at a time. The star Epsilon Aurigae is a master of this celestial magic trick. For most of its 27-year cycle, it shines as a bright, unremarkable point in the constellation Auriga. Then, something extraordinary happens. Over a period of several months, its light begins to dim. It does not flicker, it steadily, inexorably fades away. Within a year, it has lost nearly 2/3 of its brilliance. It remains in this deeply shadowed state for an astonishing 18 months, a full year and a half of profound darkness, before just as slowly returning to its normal brightness. This is not the quick wink of a planet passing in front of its star. This is an eclipse of epic, ponderous scale. The culprit is not a simple companion star, but a vast, opaque disk. Astronomers believe Epsilon Aurigae is a binary system, where a massive, luminous star is orbited by a mysterious, dark companion. This companion is not a star we can see. It is shrouded by a colossal, thick disk of dust and gas, a cosmic sombrero millions of miles wide. Once every 27 years, the geometry aligns perfectly, and this dusty disk glides directly between the bright star and our telescopes. The disk is so dense and extensive that it blocks an immense portion of the primary star's light for the entire duration of its transit. We are not seeing a small shadow, we are witnessing an entire celestial structure, a dark continent of debris drifting silently across a distant sun. Epsilon Origi's performance is spectacular, but it is not alone. An even more extreme case emerged from data from the Vista telescope in Chile, monitoring the star-dense bulge of our galaxy. Astronomers found a star now known as VVVWIT-08. Its behavior was bizarre. Over a period of 200 days, its light dropped by an incredible 97%, nearly vanishing completely before slowly recovering. This was not a gradual fade like Epsilon Origi, it was as if someone threw a switch. The best explanation is a similar, yet even more extreme, setup, a massive, irregular cloud of debris, perhaps from a shattered planet or a vast swarm of comets, orbiting a companion object in a wide, tilted orbit. When this jagged, opaque shroud passed in front of the star, it simply snipped the light off at the source. These stars, eclipsed by prolonged dust shells, represent a different kind of hidden. They are not intrinsically faint or far away. They are bright beacons that are periodically and completely shrouded. Their long, deep eclipses mean that for years or even decades, they effectively cease to exist in the visible sky, only to re-emerge as if from nothing. They teach us that the cosmos is filled with unseen architectures, immense structures of shadow that drift on silent orbits, capable of blotting out entire suns and reminding us that even the most constant points of light can hold secrets of profound and temporary darkness. Those prolonged eclipses are a temporary vanishing act, but the deepest form of cosmic hiding is not a trick of shadow. It is a simple, crushing fact of distance. To understand this, we must look at humanity's most profound photograph, the Hubble Ultra Deep Field. At first glance, it appears as a speckled tapestry of faint, colorful smudges scattered across a tiny, dark patch of sky. The scale is almost impossible to grasp. That patch is no larger than a grain of sand held at arm's length, an insignificant pinprick in the celestial dome. Yet within that minuscule void, Hubble found not emptiness but a universe teeming with light. Nearly every one of those 10,000 smudges is not a star but an entire galaxy. Each of those galaxies contains, on average, over 100 billion individual stars. The numbers become meaningless, a sea of suns so vast it numbs the mind. And here lies the ultimate act of cosmic concealment. Within that iconic image, there is not a single discernible star that is not part of our own Milky Way. Every other point of light is a galaxy, a collective glow of hundreds of billions of individual stellar fires merged by unimaginable distance into a single, fuzzy pixel. Think of a sprawling city viewed from an airplane at night. You see a dense, glowing patch of light, a single entity. You cannot pick out individual streetlights, cars, or windows. Their combined illumination blurs into one. The Hubble Ultra Deep Field is that aerial view of the cosmos. Within each of those galactic cities, trillions of individual stellar lives with their own planets, potential histories, and destinies are forever hidden from our sight, their identities lost to the void. The most extreme examples are the faintest, reddest smudges in the image. These are galaxies whose light has been traveling for over 13 billion years, stretched by the expansion of the universe into the infrared, a phenomenon called redshift. Their light is so ancient it shows us these galaxies as infants caught in the act of formation. In these blobs, we are not even seeing the full structure of a mature galaxy. We are seeing the collective glow of its first, frantic bursts of star formation. Millions of brilliant, massive, newborn stars are being born and dying in violent clusters, but their combined output is smeared by time and space into a single, diffuse point of light. We are witnessing the combined birth cries of an entire stellar generation, yet we cannot hear a single voice. This is the final, humbling truth of hidden stars. For all our technological might, our vision has limits imposed by physics itself. The universe can present us with the sum total of its glory, a census of galactic cities, while forever keeping the individual citizens, the countless stars within them, secret. The ultra-deep field is not just a picture of what we can see. It is a map of our blindness, a beautiful testament to the infinite layers of reality that remain, and may always remain, just beyond our grasp. Distance merges the light of billions into a single galactic glow, but sometimes the cosmos offers a loophole, a singular chance to pick out one voice from that ancient choir. This brings us to the farthest individual star ever seen, a point of light so distant its name feels like a whisper from the void, WHL 0137LS, known more poetically as Earendel. Its discovery shattered every expectation, for it is not a galaxy or a quasar, but a single, massive star whose light has traveled for 12.9 billion years to reach us. We see it as it was when the universe was a mere 7% of its current age, a time so remote that light from most stars of that era is hopelessly blended together. Earendel should be, by every right, completely and utterly invisible, a single candle lost in the glare of a distant city. Its revelation required a perfect cosmic alignment, a natural telescope of unimaginable power. Between us and Earendel lies a massive cluster of galaxies whose collective gravity warps space-time like a lens. This gravitational lens magnifies the light from objects behind it, but it does so unevenly, creating ripples and lines of extreme magnification called caustics. Think of sunlight dappling the bottom of a swimming pool, where the wavy surface focuses light into intense, shifting lines. Earendel, by a stroke of astronomical fortune, was positioned directly on one of these cosmic caustics. The lens did not just brighten it slightly, it amplified its light by a factor of thousands, stretching and bending its image into a long, thin arc. Without this precise, natural magnifying glass, Earendel would have remained forever hidden, its light far too feeble for any telescope to ever detect. Analysis of its stretched light reveals it was a monster, a star likely more than 50 times the mass of our Sun and millions of times brighter, a blue supergiant burning at a ferocious temperature. It lived a short, violent life and died in a cataclysmic supernova billions of years ago. We are not seeing it now, we are catching the last echo of its brilliant, fleeting existence, a snapshot from the cosmic dawn. Earendel is a miracle of geometry and gravity, a star that is only visible because the universe itself bent its rules, offering us a fleeting, focused glimpse of a single fire in the profound dark of the early cosmos. Earendel's solitary brilliance was a cosmic fluke, a single star magnified from the deep past. To find a different kind of hidden multitude, we need only look closer to home, into the ancient heart of our own galaxy. Orbiting the Milky Way's halo are dense, spherical swarms known as globular clusters, each containing hundreds of thousands of stars bound together by gravity. From a distance, clusters like Omega Centauri or M15 appear as beautiful, fuzzy balls of light, but their serene appearance is an illusion of scale. Venture into the core of one of these clusters, and you would find a stellar environment of almost unimaginable density. Picture our night sky with a few thousand visible stars scattered across the vast black dome. Now compress all those stars into a sphere just a few light years across, and then multiply their number by 100. That is the reality inside a globular cluster core. The stars here are not spaced by light years, but by mere light weeks or even light days. If our Sun resided in such a core, our nearest stellar neighbor would not be over 4 light years away like Proxima Centauri, but potentially closer than the orbit of Pluto. The sky would be a perpetual, blinding daylight, filled from horizon to horizon with stars brighter than Venus. This extreme crowding creates our 11th category of hidden stars, those lost in the stellar traffic jam. Even with our most powerful telescopes like Hubble, the central regions of the densest globular clusters present an insurmountable challenge. The light from millions of individual stars blends together into a single, blazing, unresolved core, a luminous soup where pinpoint identities are completely lost. It is like trying to distinguish individual faces in a tightly packed stadium crowd from a mile away. All you see is a shifting, collective mass. Astronomers can study the outskirts of these clusters, where stars are more spread out and resolvable, but the precise inhabitants of the inner sanctum remain mysterious. We know they are there, we can measure their combined gravity and their overwhelming glow, but we cannot pick them out one by one. This crowding leads to bizarre stellar phenomena like frequent close encounters and collisions. Binary star systems can be torn apart, new binaries can be formed by gravitational capture, and ancient blue straggler stars looking suspiciously youthful might be born from stellar mergers. Yet the exact choreography of this dense dance remains hidden within that unresolved core of light. These clusters are cosmic beehives where the frantic activity of thousands of individual lives merges into a single, brilliant, and impenetrable hum. They remind us that in the universe, sometimes the secret to hiding is not to be faint or far away, but to be one among a brilliant, indistinguishable crowd. The brilliant, crowded cores of globular clusters hide stars in a collective glare, but there is another place where a star's own future can shroud it from view. Deep within stellar nurseries like the Orion Nebula, new stars are being born, but we cannot see them with our own eyes. These infant suns are swaddled in thick, swirling cocoons of gas and dust called protoplanetary disks. These disks are not mere decoration, they are the active construction sites for entire solar systems, the raw material from which planets will coalesce. And in the process of building worlds, they perform a perfect act of cosmic concealment. In visible light, the central newborn star is completely blocked by this orbiting storm of debris. Its brilliant light, which would normally shine across light years, is absorbed and scattered by countless trillions of dust grains, rendering the star itself a dark secret at the heart of a luminous nebula. We know it is there only by its effects, by the way it heats the surrounding disk, and by the powerful jets of material it often shoots out from its poles. To pierce this dusty veil, astronomers must again look in infrared light. Infrared radiation, with its longer wavelengths, can pass through the dust much more easily than visible light. When we point an infrared telescope like the James Webb Space Telescope toward these nurseries, the hidden landscape is revealed in stunning detail. What appeared as a dark void in optical images suddenly glows with the warmth of the embedded star, its light having traveled through the disk as heat. The disk itself, once an opaque barrier, is often seen in silhouette against the brighter glow of the nebula behind it, appearing as a dark, compact shadow with a bright rim. The most famous of these silhouettes is perhaps the proplyds or protoplanetary disks in the Orion Nebula, captured beautifully by Hubble. They look like tiny, black smudges with glowing edges, each one a star and its potential planetary system in the making, caught in the act of hiding. These objects are a profound reminder of a star's earliest chapter, a time of chaotic, dusty formation when the very process of creation demands invisibility. The star is hidden by the essential ingredients of its own future family, a cosmic parent veiled by the crib it is building for its children. Mara is a star with a heartbeat, a slow, rhythmic pulse that governs its very visibility. Located in the constellation Cetus, this long-period variable star undergoes one of the most dramatic transformations in the sky. For most of its 332-day cycle, Mara is a faint, hidden pinprick, completely invisible to the unaided eye and requiring a telescope to even glimpse. Then, over the course of several months, it begins to stir. Its outer layers swell and heat, causing it to brighten by a factor of over 1,000 times. It surges from obscurity to become one of the brightest stars in its constellation, a beacon that seems to appear from nothing. This brilliant phase is fleeting, lasting only a few weeks before the star begins its long, slow fade back into cosmic shadow. The mechanism behind this incredible performance is a delicate and unstable balance within the star itself. Mira is a red giant in its final stages of life, a swollen, aging sun. Its outer atmosphere is not stable but pulsates in and out like a vast cosmic lung. As it expands, it cools, which allows certain elements in its atmosphere to condense into dust, literally forming a sooty cloud that shrouds the star and blocks its light. This is the moment it vanishes from our view. Then, trapped heat and pressure build beneath this dusty shroud until they overcome the star's gravity, blasting the material away and allowing the brilliant core to shine through once more. The cycle then begins anew. For centuries before its pattern was understood, Mira was a celestial mystery, a star that would appear and disappear on a schedule known only to the heavens. It is a periodic ghost, a reminder that even among the seemingly fixed points of light, some stars live lives of profound cyclical change, spending most of their existence as hidden, fading embers, only to roar back to life in a spectacular, temporary rebirth. Mira's dramatic cycles of light and shadow are a performance played out on a grand, personal stage. But elsewhere in the galaxy, the act of hiding is not about the star itself, but about an impenetrable curtain drawn across its face. These are the stars hidden behind dark nebulae, and they represent a simpler yet profoundly effective form of cosmic concealment. The most famous example is likely the Horsehead Nebula in Orion, a silhouette so iconic it feels like a celestial sculpture. But to understand the power of these dark clouds, look instead to a less dramatic, more perfect specimen, Barnard 68. Through an ordinary telescope, this object appears as a small, circular hole punched cleanly out of the Milky Way. It is not a void of empty space, it is a thick, cold, and dense cloud of molecular gas and dust, a cosmic storm cloud drifting silently between the stars. Its material is so concentrated that it absorbs virtually all the visible light from the stars that lie behind it. The stars are absolutely there, shining just as brightly as their neighbors, but their light never reaches us. It is swallowed by countless trillions of microscopic dust grains, each one acting like a tiny black dot in a pointillist painting of shadow. Barnard 68 is not far away. It is a relatively close neighbor, a mere 500 light-years distant. This proximity makes its effect even more striking. It is a tangible curtain hanging in our own galactic neighborhood. The result is a perfect illusion of absence. Our eyes and telescopes map the sky by tracing points of light, so when we see a region like this, we instinctively interpret it as a place where stars are not. But the truth is the opposite. It is a place where stars are too well hidden. These dark nebulae are the universe's blindfolds, cold, silent, and absolute. They teach us that sometimes the most effective way to hide something brilliant is not to dim it or move it away, but to simply stand in front of it with an opaque, unwavering wall. Barnard 68 is a perfect, static wall of shadow, but some stars are hidden because they are in frantic, permanent retreat. These are the hypervelocity stars, cosmic projectiles flung from the heart of the galaxy with such immense speed that they are destined for the intergalactic void. Their story begins in the chaos of the galactic center, around the supermassive black hole, Sagittarius A star. In that dense stellar traffic jam, a binary star system can wander too close to the black hole's immense gravity. In a violent gravitational slingshot, one star may be captured into a tight orbit, while its companion is hurled away at a staggering speed, often exceeding 1 million miles per hour. This ejected star becomes a solitary fugitive, racing through the galactic halo, the sparse, spherical region of old stars and dark matter that surrounds the Milky Way's bright disk. This isolation is the key to its hidden nature. Unlike stars in the crowded disk or brilliant clusters, a hypervelocity star travels through profound emptiness. It is a lone, fast-moving point of light in a vast, dark ocean. Compounding this, its incredible speed means it is often moving almost directly away from us or on a tangential path, making its motion against the background stars subtle and difficult to detect. Most critically, these stars are fleeing into the galactic halo, a region already distant and faint. Their great distance, combined with the fact that many are hot, blue, and therefore inherently luminous but short-lived, makes them appear exceedingly dim from our vantage point. They do not announce themselves with pulsating beams or dramatic eclipses. They simply streak unseen toward infinity. Finding them is a triumph of modern astronomical surveys, which take precise, repeated measurements of stellar positions and velocities across huge swaths of sky. Astronomers search for that one star whose speed is an outrageous outlier, moving so fast that the Milky Way's gravity can never recapture it. Each one discovered is a smoking gun, a direct piece of evidence of a catastrophic event that occurred near the black hole millions of years ago. They are ghosts with a trajectory, fading testaments to a moment of supreme violence, leaving our galaxy forever without a trace visible to the naked eye. They remind us that the cosmos is not just a place of attraction, but also of expulsion, where stars can become exiles on a one-way journey into the eternal dark between the galaxies. Our galaxy's violent past is written in the faintest of ink, in the ghostly halos of stars it has consumed. Orbiting the Milky Way like distant, tattered moons are dozens of dwarf spheroidal galaxies such as Draco and Ursa Minor. These are not the grand, spiraling cities of stars we imagine, but ancient, diffuse relics. They contain millions of stars, yet are spread so thin that their combined light is often weaker than that of a single bright star in our own galactic neighborhood. From our vantage point deep within the brilliant disk of the Milky Way, these stars are completely invisible to the eye, not because they are dim individually, but because they are drowned in a sea of foreground stars from our own galaxy. Looking toward the constellation Draco, you see a rich field of Milky Way stars, each belonging to our home spiral. Hidden among them, like a whisper in a roaring crowd, are the ancient sons of the Draco dwarf. They do not stand out by color or brilliance, they simply blend seamlessly into the stellar background. Isolating them is a task of cosmic statistics, not direct observation. Astronomers must take incredibly deep images of the sky, counting every point of light over a vast area. They then analyze the subtle, shared motion of these stars and their distinct chemical fingerprints, which are often poorer in heavy elements than typical Milky Way stars. Through this painstaking statistical filtering, a hidden population emerges from the noise, a ghostly silhouette of a galaxy within a galaxy. These faint systems are the surviving crumbs from the Milky Way's ancient feasts, the remnants of smaller galaxies that were torn apart and absorbed by our own over billions of years. Their stars are the ultimate hidden citizens, forever orbiting within the empire that consumed their original home, their presence known only through the patient collective testimony of their motion and their ancient light. That ancient light from consumed galaxies is a whisper from the past, but our own stellar backyard holds a ghost of a different kind, a hidden star whose existence was deduced not by its light, but by the wobble it caused in another. This is the story of Sirius B, the first white dwarf ever discovered and a triumph of celestial prediction. Sirius A, the dog star, is the brightest star in our night sky, a brilliant diamond of pure white light. In the 1840s, the German astronomer Friedrich Bessel noticed something strange. Sirius was not moving through space in a perfectly straight line. It had a slight but unmistakable wobble in its path. Bessel concluded this wobble must be caused by the gravitational tug of an unseen companion, a dark star locked in orbit with the brilliant Sirius. For nearly 2 decades, this companion was purely theoretical, a mathematical ghost. Then, in 1862, the American telescope maker Alvan Clark tested a new, powerful lens. Pointing it at Sirius, he saw it. There, nestled in the overwhelming glare of the brightest star in the heavens, was a faint, steadfast pinpoint of light. Sirius B had been found, The reality of this companion is a study in extremes. Sirius A is a brilliant, hot main sequence star, twice the mass of our Sun and radiating a fierce blue-white light. Sirius B, by contrast, is a white dwarf, the collapsed Earth-sized core of a star that once burned brighter than its partner. It is the stellar corpse left behind after that star exhausted its nuclear fuel and shed its outer layers. Now it is a sphere of degenerate matter, incredibly dense and hot but tiny. Its diminutive size is the key to its hidden nature. Imagine trying to see a single, bright grain of sand placed inches away from the blazing beam of a powerful searchlight. The searchlight's glare drowns out the grain completely. That is the challenge of observing Sirius B. Even through a large amateur telescope, Sirius A is so dazzling that its light floods the eyepiece, creating a shimmering haze of diffraction spikes and scattered light that easily swallows the faint companion. Only under perfect atmospheric conditions, with a steady sky and expert technique, can an observer hope to glimpse that tiny, steadfast dot of light, a cosmic cinder orbiting a brilliant flame. Its discovery revealed a new, bizarre state of matter and a future fate for our own Sun, a hidden destiny circling the brightest star we know. Sirius B is a ghost revealed by its partner's dance, a hidden star found in the glare of the brightest light we know. But to find a different kind of celestial secret, we must turn our gaze to the opposite side of the sky, to a region defined not by what blocks our view, but by what is absent. This is the galactic anti-center, the point directly opposite the crowded, brilliant heart of the Milky Way. If you look toward the constellations Taurus and Auriga on a clear, dark night, you are facing this frontier. Here, we are looking outward through the thin edge of our galactic disk, away from the dense core. The immediate obstacle of dust is less severe, offering a clearer window into the depths. Yet this clarity reveals a profound emptiness, a different kind of cosmic hiding. The stellar density here is far lower. Instead of a thick, glowing river of stars, we see a sparser scattering, a lonely highway stretching into the void. In this sparse frontier, countless faint, distant stars are not hidden behind a wall. They are lost in the vastness. Their light reaches us, but it is spread so thin, diluted across such immense tracts of space, that individual stars simply blend into a faint, unresolved haze. They are the celestial equivalent of trying to pick out a single, distant porch light from a country road at night. Each one is present, but its identity is swallowed by the sheer, dark distance between it and its neighbors. This is hiding by isolation and faintness, a cosmic camouflage of scale. While telescopes can resolve many of these stars, their true nature as distant members of the galaxy's outer disk is often overlooked, mere background noise in our search for brighter, closer objects. The anti-center is a reminder that in the universe, something can be perfectly visible yet remain completely hidden, not by a shroud, but by the simple, overwhelming fact of being one faint point in a sea of quiet darkness. Our galaxy is not a static island, but a cannibal, and its most recent meal is still visible in the sky. The large and small Magellanic Clouds are two small, irregular galaxies that orbit the Milky Way, visible as fuzzy patches in the southern hemisphere. But their interaction with our galaxy's gravity has left a scar across the cosmos, a faint, sprawling river of gas known as the Magellanic Stream. This vast, ribbon-like structure arcs across nearly half the sky, a tenuous trail of hydrogen gas torn from the smaller galaxies over billions of years. It is a cosmic wound, a testament to the gravitational tides of our galaxy. Within this immense stream of cold, diffuse gas, astronomers suspect a deeper secret may be hidden. When galaxies interact, they do not just strip gas, they can also tear away entire stars and even small clusters from their gravitational moorings. The theory suggests that scattered along the length of the Magellanic Stream, like lonely survivors clinging to wreckage, could be isolated stars or tiny, dim stellar clusters. These would be stellar refugees cast adrift from their original homes in the Magellanic Clouds and now orbiting silently within the Milky Way's vast dark halo. They are not hidden by dust or distance in the traditional sense, but by their own profound isolation and scarcity. Imagine searching for a single, unlit boat on a dark, foggy ocean that stretches for millions of light years. The stars within the stream, if they exist, would be spread incredibly thin, their faint light nearly impossible to distinguish from the background stars of our own galaxy's halo. Their detection is one of astronomy's great challenges, requiring surveys that can meticulously map the motions and chemical compositions of millions of faint stars, looking for a small population that moves in concert with the gas stream and shares the unique elemental fingerprint of the Magellanic Clouds. Finding them would be like finding a lost tribe, confirming that galactic collisions are not just exchanges of gas, but of stellar citizens, forever changing their allegiance to a new and larger kingdom in the dark. Galaxies are not the solitary islands they appear to be. They exist in vast, gravitationally bound communities called clusters, containing hundreds or even thousands of galaxies packed into a relatively small volume of space. In these dense cosmic cities, like the nearby Virgo cluster or the immense Coma cluster, galaxies do not simply glide past one another in serene isolation. They interact, they collide, and they tear each other apart. The gravitational tides between these massive structures are ferocious, and they can rip stars right out of their home galaxies, flinging them into the void between the galactic islands. Over billions of years, this process creates a phantom population, a diffuse sea of orphan stars adrift in what astronomers call the intracluster medium. Billions upon billions of suns, each once part of a coherent spiral or elliptical galaxy, now wander alone in the immense dark. This is our 20th hidden star, or rather, a hidden ocean of them. Their concealment is a matter of profound diffusion. Unlike the dense core of a galaxy where stars are packed tightly together, these intracluster stars are spread across millions of light years of empty space. Their combined glow is not concentrated into a point or even a fuzzy patch. It is smeared into an incredibly faint, uniform haze that permeates the entire cluster. This ghostly light is so dim that it is thousands of times fainter than the natural glow of our own night sky. Detecting it is an extraordinary technical challenge, requiring hours of exposure on the world's largest telescopes and meticulous digital processing to subtract the light from every known galaxy, star, and artifact. Only then does the phantom sea reveal itself, a testament to the relentless, slow-motion violence of galaxy clusters. These stars are the ultimate cosmic refugees, having lost their galactic citizenship forever, their faint collective whisper telling a story of gravitational theft on an almost unimaginable scale. Those orphan stars drifting between galaxies are not the only lonely wanderers. Some objects never had a stellar home to begin with. Hidden Star 21 takes us back to the realm of the brown dwarf, but this time we find them utterly alone. These are nomadic brown dwarfs, rogue planets in stellar mass, drifting through the cold interstellar void without a sun to call their own. They are the ultimate cosmic vagabonds, and their hidden nature is absolute. Without the gravitational anchor of a star, they float freely in the darkness. Their primary concealment comes from their fundamental failure. They are not hot enough to sustain fusion, so they emit no significant visible light of their own. A brown dwarf adrift in deep space is a cold, dark cinder. Furthermore, without a nearby star to illuminate it, there is no reflected light to give it away, no gentle stellar glow to bounce off its atmosphere. It is a shadow moving among shadows, so how do we find something that emits no light and has no light shone upon it? Astronomers use two primary methods, both relying on the faintest of signatures. The first is gravitational microlensing. If a wandering brown dwarf passes almost directly between Earth and a distant background star, its gravity will act as a tiny lens, bending and magnifying the background star's light for a brief period. For a few days or weeks, that faraway star will appear to brighten in a specific, predictable pattern, a telltale spike caused by the invisible object's gravity. It is a ghost revealing itself only by the distortion it creates in the light of another. The second method is to hunt for their residual heat in the infrared spectrum. Even a cold brown dwarf, perhaps only a few hundred degrees above absolute zero, still glows with a faint thermal signature. Powerful infrared telescopes like the James Webb Space Telescope can scan star-forming regions and the dark spaces between stars, looking for these dim, moving points of warmth. Discoveries from surveys like the Wide Field Infrared Survey Explorer have revealed a surprising number of these free-floating objects, some with masses just a few times that of Jupiter, wandering relatively close to our solar system. They exist in a strange category, too massive to be typical planets, yet too small and cold to be stars. Their existence suggests that the process of star formation is messy, often ejecting these failed embryos into the darkness before they can fully mature. Each one is a dark, nearly invisible monument to a birth that never quite succeeded, a perpetual wanderer in the endless night between the stars. The universe was not born with stars. After the brilliant flash of the Big Bang faded, it entered a profound and silent chapter known as the Dark Ages. For hundreds of millions of years, the cosmos was a vast, featureless sea of cooling hydrogen and helium gas, utterly dark and devoid of any source of light. Then, in the deepest pockets of this primordial fog, gravity began its patient work. Slowly, agonizingly slowly, the first clumps of matter grew, collapsing under their own weight, heating up until the very core of these clouds ignited with the first nuclear fires. These were the population 3 stars, the universe's original pioneers. But if they were the first lights, why are they our 22nd hidden star? Because the universe itself conspired to smother their brilliance at the moment of birth. The problem was the medium they were born into. That sea of hydrogen gas was not transparent, it was a thick, neutral fog. Neutral hydrogen atoms are voracious absorbers of ultraviolet light, the exact kind of high-energy radiation that massive, hot, newborn stars produce in abundance. So, when those first stars finally switched on, their brilliant ultraviolet light did not travel across the cosmos as a beacon. It traveled only a short distance, perhaps a few thousand light-years at most, before it was greedily absorbed by a neighboring hydrogen atom. That atom would become ionized, its electrons stripped away, but just beyond it, another neutral atom waited to catch the next photon. The light from these first stars could not pierce the global fog. They were like lighthouses shining in a dense, perpetual sea mist, their beams swallowed whole after only a few feet. Each star illuminated only a tiny, localized bubble of clear, ionized space around itself before its light was extinguished. From our perspective, looking back over 13 billion years, that entire epoch is a uniform, opaque wall. We cannot see those individual lighthouses. No telescope, no matter how powerful, will ever capture their direct light. They are hidden behind the very substance that birthed them, yet we know they must have existed because they changed everything. Their cumulative effect over hundreds of millions of years was to eventually burn away the fog. The ultraviolet radiation from countless generations of these first stars slowly, region by region, ionized the neutral hydrogen throughout the entire universe, a process called reionization. This was the cosmic dawn, the moment the fog lifted and the universe became transparent to light. We see the end result of their work, the clear, sparkling cosmos we observe today, but the individual workers who cleared the fog remain forever shrouded within it. Their legacy is a transparent universe, yet they are the most fundamentally hidden stars of all, their brilliant births witnessed only by the silent hydrogen atoms they destroyed. Those first stars were hidden by a cosmic fog, but modern telescopes face a different kind of optical illusion, one that distorts reality itself. Among the most spectacular sights in deep space astronomy are the giant luminous arcs that curve around massive galaxy clusters. These are not physical structures but cosmic mirages, the warped and stretched images of galaxies that lie far behind the cluster. The cluster's immense gravity acts as a lens, bending the fabric of space-time and thus the path of the distant galaxy's light. The result is a smeared, often multiple image of that galaxy, stretched into a thin, bright crescent. To the untrained eye, it looks like a celestial brushstroke painted across the void. But within that single, beautiful arc lies a deeper secret, a hidden population of stars. The arc is not a solid thing. It is the combined, distorted light of billions of individual stars from that background galaxy. Each of those suns has had its light bent and magnified by the gravitational lens. In a sense, they are all visible, their light has reached us, but they are not seen as distinct points. Their identities are completely blended, warped beyond recognition, and smeared together into that single, luminous line. It is as if you took a detailed family portrait, stretched the canvas into a long, thin ribbon, and then asked someone to pick out individual faces. The information is there, but it is encoded in an impossible tangle. Astronomers can use sophisticated models to try and reverse engineer the distortion, to understand what the original galaxy looked like before the cluster's gravity worked its magic. Yet, even with our best efforts, the individual stars within those arcs remain forever hidden within the collective glow. They are prisoners of geometry, their light hijacked and contorted to create a beautiful collective illusion, a reminder that in the cosmos, seeing is not always believing, and that sometimes the most brilliant displays are the ultimate acts of celestial camouflage, hiding a multitude within a single, twisted line of light. Gravitational lenses create cosmic mirages, warping the light of distant galaxies into beautiful, unreadable arcs. But there is a much closer, more personal blind spot in our celestial vision, one dictated by the simple geometry of our own orbit. Every moment of every day, our brilliant sun acts as a perfect cosmic shield. It blocks our view of an entire cone of space directly behind it, a region that shifts slowly as Earth travels around its yearly path. Stars that lie precisely along that line of sight are permanently hidden from us, not by dust or distance, but by the overwhelming glare of our own parent star. This is a blind spot that moves, a shifting void in our star maps. As our planet completes its circuit, new stars rotate into this hidden zone, while others emerge from behind the sun's limb, as if being born anew into our sky. The concept is elegantly simple, yet its implications are profound. It means our census of the nearby cosmos is inherently incomplete. There could be a dim red dwarf, a quiet brown dwarf, or even a rogue planet with rings, sitting almost next door in cosmic terms, and we would have no way of knowing it was there through direct observation. Our most powerful telescopes are useless against this obstacle. You cannot peer around the sun. The only way to infer what might lie in that zone is through indirect means, like detecting a subtle gravitational tug on the orbits of known objects, or waiting decades for our motion to finally slide that patch of sky into view. This is a hiding place defined by pure orbital mechanics, a reminder that our perspective on the universe is not just limited by technology, but by our fundamental location in space. We are forever looking out from behind a brilliant, unwavering searchlight, and we can only wonder what secrets lie hidden in its permanent, shifting shadow. Our sun's glare creates a moving blind spot, but even when we can look directly at a star, its closest secrets can remain invisible. In the crowded stellar neighborhoods of our galaxy, most stars are not solitary. They exist in pairs or even triple systems, bound together by gravity in an endless dance. Often, these partners are easy to spot, two distinct points of light separated by a clear gap. But there exists a more intimate and elusive class of binary, where the stars are so incredibly close together that even the most powerful single telescope in the world sees them only as a single, unremarkable point. The companion star is not just dim, it is orbiting so tightly that its light is completely drowned in the overwhelming glare of its brighter partner. For centuries, these faint companions were perfect secrets, hidden not by cosmic dust, but by the fundamental limits of optical resolution. A telescope's ability to see fine detail, to separate two close objects, is governed by the size of its mirror. Even the colossal mirrors of our greatest observatories have a hard limit, a blurring effect caused by the wave nature of light itself. When two stars orbit only a few milliarcseconds apart, a tiny fraction of a degree on the sky, their light blends into one indistinguishable blob. The fainter star is simply swallowed whole. Unmasking these hidden partners requires a brilliant workaround, a technique that effectively creates a telescope as wide as a continent. This is optical interferometry. Instead of relying on one giant mirror, astronomers combine the light collected by two or more telescopes separated by a vast distance. By precisely timing the arrival of light waves at each dish and merging the signals with exquisite accuracy, they can simulate the resolving power of a single telescope as large as the distance between them. It is like using the separate ears of a giant to pinpoint the faintest whisper in a roaring crowd. For a binary star, this means the subtle interference patterns in the combined light can be decoded to reveal not one but two distinct sources. The technique can measure the minuscule separation, the orbital motion, and even begin to tease apart the individual characteristics of each star. Until very recently, these tight binaries were cosmic mysteries, their dual nature completely concealed. Now, thanks to interferometry, we are pulling back the curtain on stellar relationships of incredible intimacy, revealing hidden companions that have been dancing in plain sight, their secret lives finally coming into focus. Our entire perspective of the cosmos is framed by the ground beneath our feet. For half the world's population, the most spectacular part of our galaxy is a permanent secret. If you live north of the equator, the very heart of the Milky Way, its brightest and most star-packed regions, never rises above your horizon. This is a hidden sky dictated by simple geography. The Milky Way is a flat disk, and our solar system is embedded within it. When we look toward the constellations Sagittarius and Scorpius, we are staring toward the dense, brilliant core. But from a city like New York or London, that core skims just along the southern horizon, if it appears at all, often lost in atmospheric haze and light pollution. To truly see it, you must travel south. From the southern hemisphere, the galactic center climbs high overhead, transforming the night. The Milky Way is no longer a faint, hazy band. It becomes a breathtaking river of light, so dense with stars it casts shadows on the ground. Within that river, you can see with the naked eye the dark lanes of interstellar dust, the glowing pink nebulae of stellar nurseries, and the concentrated glow of millions upon millions of distant suns in the central bulge. For a northern observer, these sights are not just difficult to see, they are fundamentally inaccessible, hidden by the curve of the Earth itself. Billions of stars that are prominent landmarks in a Chilean or Australian sky are, for someone in Canada or Germany, permanently below the ground, lost in the same way the sun is lost during night. This cosmic hiding place is a profound reminder that our window on the universe is not just limited by technology or physics, but by the accidental coordinates of our birth. The full majesty of our home galaxy is a privilege of latitude, a hidden masterpiece half the world has never truly seen. The Earth itself casts a shadow that can hide the stars, but what if our planet also trails a faint cosmic dust cloud? At two special points in space, known as the Lagrange points L4 and L5, gravity and orbital motion create zones of stability. These are places where the gravitational pulls of the Earth and the Sun balance perfectly, allowing objects to essentially park there. In the 1960s, a Polish astronomer named Kazimierz Kordylski proposed that these points might not be empty. He suggested they could hold vast, tenuous clouds of fine dust, particles perhaps left over from the solar system's formation or captured from the endless stream of interstellar grit. These hypothetical formations are now called the Thorne-Żytkow clouds. They are not solid objects, but the faintest of veils, more like a permanent, diffuse haze of microscopic particles held in place by celestial mechanics. Their existence has been debated for decades, with some observations hinting at their presence, while others find nothing but empty space. The challenge is their profound faintness. They do not glow, they only scatter a tiny amount of sunlight, making them millions of times dimmer than the Gegenschein, the already faint glow sometimes seen opposite the sun in the night sky. If these clouds are real, they represent a hiding place of astonishing intimacy. They would mean that as we gaze out at distant constellations, the light from some of those stars passes directly through a permanent, ghostly shroud within our own solar system. A star shining from behind a Thorne-Żytkow cloud would be very subtly dimmed, its light filtered through a fog of ancient dust that orbits in tandem with our own world. This is not hiding by distance or brilliance, but by the most delicate of occlusions, a whisper-thin curtain hanging at a gravitational crossroads just a step away from Earth. It suggests that some of the stars we chart might appear just a fraction fainter than they truly are, their light softened by a secret we carry with us through space, a barely their companion clouding our view from right here at home. The most profound act of cosmic concealment may be the act of creation itself. Before a star ever shines, it spends its earliest life in a state of perfect darkness. These are the Class 0 protostars, stellar embryos so young and deeply shrouded they represent the ultimate hidden star. The process begins in the cold, silent depths of a molecular cloud, a vast nursery of gas and dust. Here, a dense knot of material, perhaps triggered by a shock wave from a distant supernova, begins to succumb to its own gravity. It starts to collapse. This is the moment of stellar conception, but it is a birth that happens in utter secrecy. The infant protostar is not yet a star at all in the conventional sense. It has no internal fusion. Its only heat comes from the violent conversion of gravitational energy into thermal energy as it shrinks. All of this furious activity is buried under an immense, cold, and opaque envelope of its own parent material. Imagine a tiny, hot ember at the very center of a snowdrift the size of a mountain. The ember glows, but its light cannot possibly penetrate the thick, frozen layers surrounding it. For a Class 0 protostar, the envelope of gas and dust is so thick that it absorbs every single photon of visible light the core might emit. To our optical telescopes, even the most powerful ones peering into famous nurseries like Orion, these objects are completely and utterly invisible. They are not dim, they are absent. Their existence is betrayed only by the faintest whispers in a language of light we cannot see. As the core heats up, its warmth causes the surrounding dust to glow, but not in visible light. It radiates in the far infrared and submillimeter wavelengths, and even emits faint radio waves. Detecting a Class 0 protostar requires us to listen to these cold, long wavelength signals. Astronomers use specialized radio telescopes, like the Atacama Large Millimeter Array high in the Chilean desert, which act as cosmic stethoscopes. They tune into the faint thermal rumble of cold dust and the specific radio signatures of molecules like carbon monoxide spinning and tumbling in the dense envelope. What they reveal is not a picture, but a map of warmth and density, a shadowy outline of a cocoon with a violent, hidden heart. These objects are stars in the womb, their brilliant futures still locked away behind a veil of their own making. They remind us that every beacon in the night sky began its life as a secret, a hot, dark promise buried in the cold dust of a cosmic cloud, invisible until the moment it was ready to tear its way into the light. Andromeda is a mirror held up to our own galaxy, a swirling island of light 2.5 million years away. Through a telescope, its spiral arms are a breathtaking sight, a whirlpool of billions of suns. Yet woven through those luminous arms are thick, dark ribbons, dramatic dust lanes that carve shadowy canyons through the stellar glow. These are not empty spaces. They are the same kind of interstellar soot that creates our Milky Way's own dark rifts, like the Great Rift in Cygnus. Every one of those dark lanes in Andromeda is a wall. Behind that wall, the light of countless stars is being absorbed. We see the grand architecture of the galaxy, its overall shape traced by the stars we can see, but we must remember that its full population remains a mystery. For every brilliant star along the edge of a dust lane, there could be a dozen more directly behind it, their light forever lost to us. We map Andromeda by its visible points, but its true stellar census is hidden in those silhouettes. This neighboring galaxy, so close we can study individual star clusters within it, still keeps fundamental secrets about its own citizens, obscured by the very dust that helped to form them. It is a poignant reminder that even our clearest views of the cosmos are partial, filtered through curtains of our own galactic making. Our own sun did not form in isolation. It was born in a stellar nursery, a giant, collapsing cloud of gas and dust over 4.6 billion years ago. Within that fertile chaos, it was not the only star to ignite. Hundreds, perhaps thousands of sibling stars burst into life around the same time from the same primordial ingredients. For a few million years, this family of infant suns would have shone together in a relatively tight cluster, a brilliant, temporary jewel in the young Milky Way. But star clusters are not permanent. The gentle yet relentless tidal forces of the galaxy's rotation and the gravitational nudges from passing gas clouds and other stars slowly but surely pull them apart. Over billions of years, the cluster dissolves. Its member stars are scattered like dandelion seeds on a galactic wind, each embarking on its own solitary journey around the galactic center. Today, our sun's brothers and sisters are everywhere and nowhere. They orbit the galaxy on paths similar to our own, but they are completely lost to us. This is our 30th and final hidden star, or rather, a hidden family. They are the sun's long-lost siblings, and they are hidden in the most frustrating way possible. They look exactly like every other star. To our telescopes, a stellar sibling of the sun appears as a completely ordinary, middle-aged yellow dwarf star, utterly indistinguishable from the hundreds of billions of other similar stars in the galactic disk. There is no label, no unique glow, no special signature in its visible light that says, "I was born with your sun." Finding them is perhaps the ultimate cosmic detective story, a case solved not by looking at what we can see, but by analyzing what we cannot. Astronomers hunt for them using two incredibly precise forensic techniques. The first is chemical tagging. Stars born from the same cloud share an identical chemical fingerprint, a specific ratio of elements like iron, oxygen, and magnesium that is as unique as a family recipe. Our sun has a specific recipe. By using high-resolution spectrographs to analyze the light of sun-like stars with exquisite precision, scientists can search for stars whose elemental abundances match our sun's to an uncanny degree. The second clue is dynamical. Stars that were born together will, even after being scattered, retain a memory of their original motion. Their orbits around the galaxy will share similar characteristics, a common velocity and direction that traces back to that single point of origin billions of years ago. By combining precise chemical analysis with precise measurements of a star's motion through space, astronomers can identify candidates. A handful of potential siblings have been proposed over the years, stars like HD 162826 and HD 186302, which share our sun's chemical makeup and a similar galactic orbit. But the search is extraordinarily difficult, like trying to find a few specific grains of sand on a beach that spans a continent, when every grain looks nearly identical. The family is lost in the crowd. This final hidden star reframes our entire place in the cosmos. We are not a solitary wanderer. We are one member of a vast, scattered family, a family whose reunion is impossible, whose members pass us silently in the dark every million years, unknown and unrecognizable. The night sky is not just filled with strangers, it is filled with our own kin, forever hidden in plain sight. From the cold, silent brown dwarfs drifting in our own cosmic backyard to the brilliant, fog-shrouded giants of the cosmic dawn, the universe is a master of concealment. This incredible diversity of hidden stars forms a parallel reality to the night sky we know, a grand and unseen tapestry woven from gravitational ghosts, dusty cocoons, and the cold embers of stellar corpses. Each category, from the violently expelled hypervelocity stars to the patient, periodic vanishing of Mera, reveals a different law of physics or a chapter of cosmic history written in the language of absence. These are not mere gaps in our knowledge, they are positive evidence of a richer, more dynamic, and often more violent cosmos than our eyes alone could ever perceive. This relentless drive to find what is hidden is the engine of human curiosity. It pushes us to build telescopes that see in heat and radio waves, to craft algorithms that filter starlight for chemical whispers, and to launch observatories beyond the distorting veil of our atmosphere. Every hidden star is a puzzle that demands a new way of seeing, forcing innovation and expanding the very boundaries of our perception. So the next time you stand beneath a clear, dark sky, let the familiar constellations anchor you. But then, let your mind wander into the spaces between them. In that profound darkness, remember the vast multitude that science assures us is there, the failed stars, the stellar cannibals, the ancient pioneers, and the scattered siblings of our own sun. They exist just beyond the edge of sight, in a hidden universe of wonders waiting to be revealed.